The loan prediction problem is a binary classification problem. Being a binary classification, it's either a 0 or a 1. So it's either a 0 or a 1, or a yes or a no, or either a reject or accept. Yeah, or head or tail and stuff like that. So what we do with the loan prediction problem is also a kind of a binary problem, since we either want to accept or reject a borrower. So with the binary classification problem, there are certain steps that you have to follow when you are doing such kind of analysis. So, and we'll mostly use the logistic regression model, since it's usually the best for one of the best for working with binary classifications. And you can actually clearly explain to people why, for example, if they are not able to get a loan, tell them a variable is actually pulling you down, or work more on this variable, that it will help you more. So with that, let us go through the table of contents. Basically, what we're going to do is just define the problem, generate hypothesis. So hypothesis generation basically is, we want to test, for example, whether, for example, gender, is it usually useful when classifying a loan, for example, male or female? What's your likelihood of getting a loan? And test some of the hypotheses, like if you have this number of children, how likely to be able to get a loan? Or if, for example, if you have a spouse and you have declared the income of your spouse, how likely are you to be able to get a loan depending on the income of your spouse? So with hypothesis generation, we are just going to look at our data and try and answer some of the questions using the data. That will actually help when you're generating variables to help with the logistic regression. So basically, after hypothesis generation, we are going to do exploratory data analysis. Univariate analysis is when we are looking at one single variable. Bivariate analysis is when we are looking at one variable versus the dependent variable. So the dependent variable will be, in our case, we'll use either accepted or rejected. So that will be the dependent variable. So, and then we look at the missing values or outlier treatment. So outliers are basically, for example, if we expect a loan to be within a range of 1,000 to 10,000, but an outlier might be 50,000. So that's an outlier. And missing values are those that, for example, we have male and female, and we have certain missing values. In that case, we might look at how we are going to fill in those missing values. And then we'll go to model building. We'll be using the logistic regression, and then we'll look at the evaluation metrics for, basically we'll use for classification problems. Basically, these are what you'll use for most classification problems, the metrics. So let's go to the problem statement. So we have let's say we have a fictitious company that offers loans to people. They have presence in urban, semi-urban, and rural areas. So customer first apply for a home loan after the company validates the customer eligibility for the loan, whether they have, let's say when you are applying for a loan, you have a certain eligibility. For example, you have 18 years. That's what we are actually looking at. So the company wants to automate the loan eligibility process. That's basically what we also do for mobile. Basically, most of the stuff is just automated. You apply, you're either accepted or rejected. So The details of these variables are like gender, marital status, education, number of dependents, income, loan amount, credit history, and some of the others we'll also discuss. So to automate this process, they have to identify the customer segments and those eligible for the loan amount so that they can specifically get the customers. So let's go to the hypothesis generation. So basically, most of your data science career, or if you want to do anything to do with analysis, you're going to generate usually a lot of hypotheses. You're going to mostly test a lot of hypotheses when you want to deal with data. So either, for example, customers of this age have certain characteristics and they are more likely to default. So those are the kind of questions you have to continuously ask yourself when you're dealing with data science problems and most of the analysis problems. You have to continuously ask yourself questions. So if I may ask, what kind of questions do you think we might ask for such a problem? If I can get some of your feedback. Don't know if any more. So these are the questions that we are going to ask for in our case. So the salary. So this is, we'll either look at whether applicants with high income have a higher chance of loan approval, or whether the applicants with the lower income will be rejected more. So the reason we'll be asking this question is because we all know that somebody with a higher disposable income will be more likely to pay a loan. So another question we might love to ask is the credit history. For example, whether an applicant that previously paid their loan, how likely are they to default on their borrowing? So the loan amount. So we'll basically look whether the applicant will be accepted or rejected based on the loan amount. A higher loan amount, does it mean that we are more likely to be rejected, or does applying for a lower amount mean that your likelihood of being rejected reduces? So that's why we'll be looking at the loan amount. So the long term, basically what we want to know is whether the longer your long term, how likely are you to be approved, or the shorter your long term, how likely are you to be approved or rejected. So basically those are some of the questions you're going to ask. So I'll also type for you here question. What are some of the high So I have typed for you a question, so anyone can just respond as we continue. So we get here where we import some of the libraries for Python. There will be pandas, we'll use NumPy, Seaborn, and Matplotlib are basically used to plot data. This one basically means we want to, afterward it will plot inside the Python notebook. When we don't put this line, it means it will open another tab to plot data. So when you run that, you just hit Control Enter. You'll be able to run your notebook. Yeah, Jamal, actually that's a very good question. Is loan status affected by education? That's a very good question. because what basically we might look at are your education levels. Whether you're somebody who has a PhD is more likely to be accepted or to be approved, or somebody who went to primary is more likely to be approved or rejected. So actually that's a very good question. And yeah, for Peter, that's also a good question. The married people, we want to see whether you having a co-applicant, are you more likely to be accepted or rejected? Because that basically means it gives you more money to actually pay for the loan when you have declared your co-applicant's income. So those are actually very good questions, and they are actually used to in making decisions for actual real loan problems. So we'll import the train and test datasets. So the train dataset, we are going to use it to train the model, while the test dataset, we are going to use it to evaluate the final model. So we make a copy so that we avoid any accidental changes for the data. So it's always a good practice. Once you have imported your data, just always make a copy of it, as it will help you in case you change some variable and you're not able to get it back. It helps a lot when you just easily revert to the data. So we run that by control enter. So this one, we just want to view variables. So we can either put the head, or we can change this to tail to view the last 10 rows for a trained dataset. So as you can see, we have the loan ID, gender, marital status, whether you are married or not. Okay, so I can see Susan has also typed whether self-employed are more likely to get loans approved compared to actually that's also one of the main things, because most of you, when you actually apply for a loan in a bank, they'll actually ask you for your either for your salary, for your payslip, or for your business. They look at the amount of income you generate or the profit you generate. So that's also a very good answer. So that's also a very good answer. That's one of the main things actual people look at. So we'll be viewing our columns. Just write the train column. So when you are looking for anything in Python, when for example I write a train and then dot columns, this means I'm accessing, for example, like a function in pandas to view the columns. Once anything that will make a change on the dataset, you'll put the brackets. Anything that is dependent on the data set, for example, the rows, the columns, you just write, for example, train.columns if you want to view the column names. Sorry. So we have gender, marital status, which Peter had suggested, dependents. The dependents are the number of children that you have, and then there's the education. So Tim has also asked a very good question. Does the department I work affect the loan approval? E.g., I am in the sales department, I am less likely. E.g., if I am in the sales department, I am less likely to get a loan than somebody in the HR. For that, I don't think your department will really matter, because you might be in the sales department, but you are actually making a lot of money in the sales department, or you might be in the HR department, but you are making a lot of money in the HR department. So I don't really think that will matter. Basically, but to some extent also when we are declaring, for example, a profession. For example, when you compare a doctor, an engineer, when you're actually comparing professions, it might make sense when that data is provided. But you see, in most cases, most people don't even provide data regarding their professions. They'll only put in the salary and from which organization they get the salary from. So these are the columns. Yeah. So it will depend. So when you are looking at sales guys, it's more of, let's say it's more of like a normal distribution. You are less likely to get earning so much money compared to the probability of also getting a doctor earning so much money. So like when you put them in a normal curve, you'll notice most sales guys are in the, like, let's say it's just kind of skilled, but that's also just an hypothesis. If we had data, we might test it. That's why I was telling you, generating your hypothesis is just as important as analyzing your data, because it will also determine kind of variables and how you're going to actually design your variables. So we'll look at the test columns. They're actually almost the same with the train columns, except for the test columns do not have the loan status. As we are going to, this is for the test columns, this is what we are going to predict. So that when you run that, you'll notice it doesn't have the loan status. So we look at the dimensions of the data. So dimensions basically looking at the shapes, the number of rows versus the number of columns. So for the trained data set, we have 614 rows and 13 columns, while for the test data set, we have 367 rows and 12 columns. So this is because we want more data to be used to train than to test. As the bigger your data that is used for training, you will have a more accurate prediction compared to having a small data set used for training. So we'll look into exploratory data analysis. This is the univariate analysis. So univariate analysis, basically what you're going to do, we are just going to look at one variable that we'll go variable by variable. So that's the thing with doing analysis. You have to really understand your data set per variable. For example, if you have 15, you have to look at all the 15. If you have 20, you basically have to look at all the 20. So this is usually the simplest. We are just going to create basically the normal stuff like the mean, median, mode, and basically plotting the graphs and see how the distributions for certain variables, for example, for loan status, we're just going to see how it's distributed across the data set. And remember, it will be a trained data set. So for that, we can see there are 422 that were approved versus 192 that were not approved. So when you set the normalized is equals to true, this is when we want to get the percentages, like 68% were approved. So when you are dealing with the single variables, it's usually most advisable when you tell somebody percentages, since when you give somebody raw figures, for example 422, it's usually not very easy to understand. So it's better when you tell them 68% of these loans were approved versus 31% that were not approved. So it's usually advisable to use percentages or use visual things like graphs. So we'll plot the loan status and the values, and we'll see, as you can see here, there are more were approved, those that were rejected. So after this, we're just basically going to plot the whole set of variables like gender, married, self-employed, history, and the loan status. And then we look. So you can see gender. As you can see, the distribution, our data set has more males than females. Married, our data set has more married people than not married. Self-employed, our data set has less self-employed people than those that are employed. And credit history, our data set has like 85% that had repaid their loans compared to 15% that had not repaid their loans. So, and for credit history, we actually expect this, as it would not be a good thing when most people that did not repay their loans actually apply for loans. So these are just basically the summaries that we are talking about above there. So the independent variables, we can look at the number of dependents, the education, and the property, whether okay, sorry there, let me just run this. So the property area will mean where the applicants are from. So these are the number of dependents. We can see the highest number of people don't have any dependents. For 1 and 2, the percentages are almost the same, and the lowest are those with 3 dependents. For education, we have graduate. Most of the people are graduate level compared to not graduate. Semi-urban property area will be those from semi-urban, urban, and rural. This is almost akin to like where you're from. You can basically use mainly GPS coordinates to get those and actually just infer the kind of places the GPS coordinates are from. So we'll go to the numerical variables. These are like the applicant's income. So applicant's income, basically we expect most people are, this is one of the places where most of this income disparity. I don't know how many of you know of when, for example, when you look at an organization, you notice most people are paid, let's say, towards the center. There are very many people that are paid, like it basically is left skewed. An organization will have more people being paid in the lower side compared to the upper side. Mostly management gets paid on the upper side. That's why we can look at the applicant's income. Basically, it looks like it's skewed to the left. So when you do a box plot, you can see that there are more on the applicant's income. That's why we see it's actually skewed. So basically, when you do things like any numerical variable, it's usually best when you do like logarithm, when you transform the variable. The reason why you need to transform it is because you need it to follow a normal distribution. So as you can see, most of the applicants' income is towards the left. That's usually expected also in most places. Most of the applicants' income will be towards the left. So here we'll compare applicants' income by education. So as you can see, most graduate people, you are more likely to get outliers in graduate people compared to those that are not that did not graduate. I had seen somebody had given a reason for education level. Education level will be one of the one. Yes. Jamal had talked about education level. So as you can see here, education level will also be one of the main areas you'll be looking at. Here, you are more likely to get people that are graduate level having higher incomes compared to those that did not graduate. So here you can look at the core applicant's income. So for the core applicant's income, it's also the same. You are more likely to get people in the lower side, but let me also give you a question. What kind of distribution does the core applicant income have? Distribution does the core income have? And we go to here some of your responses on that. Because you can see for the core applicant's income, for example, here we can basically see it also has a lot of. So let's go to the loan amount. Okay, the loan amount, this one, actually this is, we can see most of the applicants actually taking loans in the middle, let's say 150. Most of the applicants are taking loans in the 100 to 150 range. So when you look at something like this, you can also infer the kind of population that you have. So after that, let's go to the bivariate analysis. So here it's where we'll be looking at the hypothesis that we had previously asked ourselves, like applicants with high income, should they have high chances of loan approval? So let's start here also with gender. We'll be starting with gender. So for gender, we'll be asking whether a person's gender will actually determine the status of the loan, whether they will be approved or not approved. So we can run that. So we can see here the gender for female actually have a slightly higher reason for approval. So I also have a question. Why do you think the female gender actually has a slightly higher chance of approval? Or why do you think the percentage for female approved is actually slightly lower? I'm saying it's actually slightly lower since the right one is male. So we'll actually be looking, why do you think the percentage for female not approved is slightly higher? So you can type your response. So, but basically there's not that big of a difference here, as you can see on the graph. So basically, when you look at a variable, you want a clear risk separation. What I mean by risk separation is when you are comparing, for example, male and female, you can actually see there will be a risk separation, so that when you include it in the variable, you'll actually see there's an effect. Actually, Susan, I'd actually say the main reason is, I'd say, for females, you might actually it's just more of like an hypothesis. I'd say, since considering there'll be less, there are less applicants who are female, there's not to actually like grade them. So a risk averse, for example, bank will actually, or lender will actually give them a much poorer score than male, who they have a lot of data and they actually know how they behave. So it's just an hypothesis I have. So maybe you might have a different one. So we'll visualize the remaining categories. So another thing, when you're working with most data visualization stuff, don't worry too much about the syntax. Most of it when I want a visualization, I'll just Google it, or just get it from Stack Overflow or somewhere, and you just have to understand like how to write everything word by word. Don't worry about that. With time, it usually comes. After you have done a visualization for almost so many times, it will just come to you. Don't worry about that. So let us run for all the variables. So we'll be looking at, let's start with married. So we'll look at those that are not married are more likely to be rejected compared to those that are married. So as somebody had said here, who had given an hypothesis here, those that are married are more likely to be accepted for loans. I don't know who gave that hypothesis. Yeah, Peter. I'm seeing Peter, actually he was right. So when you are married, you are more likely to get a loan compared to those that are not married. So here is the number of dependents. So for the number of dependents, we might not actually infer anything that great, since there is no clear risks. Like, what we want is either, for example, as the number of dependents increase, your risk of getting rejected is higher or lower. So as you can see here, those with no children are much more likely to be approved compared to those with one child. Those with two children are more likely to be approved compared to those with no children. So another hypothesis we might form there are those with, for example, children are more stable, but that's just an hypothesis. You just have to look into more data. And then we look at, since it's not validated by those with 3 children, so since they are just as likely to be rejected as a person with 1 child. So for graduates, those who have graduate degrees are likely to be approved compared to those with no graduate degrees. So actually, this is one of the best tables, since we can clearly see. So education, so self-employed. So for our data, for self-employed, it doesn't really make any difference whether you're employed or self-employed. So we look at the relationship with the remaining categories. Here we look at credit history. Credit history, those who have repaid a loan are more likely to get approved compared to those who did not repay a loan, and this is actually true. Property, those in rural areas are less likely to get a loan compared to those living in semi-urban areas. So we look at the loan applicant by the applicant's income, loan status by the applicant's income. So basically, when you plot the applicant's income with loan status, the mean, it doesn't really give you a lot. So basically, what we do, we usually bin the amounts. For example, we might start with 0 to 2,500, 2,500 to 4,000, 4,000 to 6,000, 6,000 to 81,000. So here we might do this. This is actually much more helpful than comparing the mean. So those who have borrowed, those who have a lower income are more likely to get rejected. This one is showing more likely to get actually accepted compared to those with a higher income. But when you're looking at, for example, in a rural situation, this one might not be the case. So when you're looking at the applicant's income, it doesn't really give us a lot of information, since it basically doesn't really affect whether you're going to get approved or rejected. So we are looking the co-applicant's income and try and see. Okay. So for the co-applicant's income, those with the low income are more likely to be approved compared to those with the high income. So for this, we might actually have to look more into our data, since this one is not kind of intuitive, as you'd expect. Somebody with a higher income is more likely to get approved compared to those with the lower income. So when we combine both, actually this might be better. When you combine the applicant's income and the co-applicant's income, so those with low income are more likely to get rejected compared to those with very high income. Actually, now this one makes much more sense compared to the first one. So this is also another thing when you're dealing with things like credit scoring. You actually have to look for variables. Like, for example, if we look at them individually, they don't make a lot of sense. But when you combine some of the variables, for example, the total income, the applicant's income and the co-applicant's income, you are actually able to see very big changes here. So this is, we actually usually call this engineering. You might actually need to do a lot of this, like looking for better variables that may actually give you a better risk separation. That's what I meant by risk separation. For example, when you compare the low income versus the average income, you can clearly see the low income are more likely to get rejected compared to those with average income. So another hypothesis, let me also ask another question. Why do you think those with high income have a higher rejection rate compared to average income? So also you can try and figure out that why, for example, the very high income are more likely to get rejected compared to the average income. So anyone can just take a stab at that. It will be good to hear your responses on that. So when you're building features, yeah, actually, Alex, that's actually true. One reason could be the expenditure might be higher. Yes, that's actually true compared to those with average income. Also, another reason might be those with actual very high income, most of them actually don't apply. So those that apply are actually those with maybe bad credit. They are more likely to get rejected. So since we saw there are a lot of outliers with the very high income, so that means also there are not also a lot of people in that area. But your reason might actually be very good. So anyone else might actually also try that. But basically, out of all this, what I want you to know is that when you are creating variables, you should always ask yourself questions, try and answer them. Like for example, it's not advisable just to use variables because it's usually used there. You have to like ask yourself questions. Why am I using this variable? Why, for example, why is it not behaving the way I expect it to be? For example, if I expect it to behave in a certain way, why is it doing that? So those are the very important questions. That's why the hypothesis generation part is usually very important. So we can also look at the loan amount. So when you look at the loan amount, you can see the low average. Higher loan amount means you are more likely to get rejected compared to the low loan amount. Also, that's also very true, since you actually expect a person that you're actually going to give out a huge amount of loan, you're going to actually tighten your policy. For example, if I'm going to give a loan to somebody for, let's say I'm giving out 100,000 compared to 10,000. For 10,000, I won't expect so much, since when I lose the amount, it won't be a huge loss compared to somebody with 100,000. So that's why you can see those with the higher loan amount are more likely to get rejected compared to those with the low loan amount. So we might also look at this. Oh, okay. That one you only need to run it once. So this is the correlation matrix. So basically, a correlation matrix actually shows you the strength each variable has against each other, and it's also very important to have a correlation matrix as it helps you to look at whether your variables are actually correlating. As two variables that have a very high correlation, you don't have to include them both in the data set when you're running the model. So basically here we see loan status has a very high correlation with the credit history. You can see here loan status is this one, credit history is this one, it's this box here. So also here go straight, and then for loan status is here. We see the correlation is a little bit higher. So another one will be loan amount with the applicant's income. So this one is also intuitive, as we expect those with a higher income to for much larger loans. So another one is loan amount and the co-applicant's income. So when you combine these two, they actually make sense. So those ones are the main ones that have high correlation. So we can look at the correlation matrix here. So this data 1, it means the correlation is 1. They are perfectly correlated. And anything that is perfectly correlated, for example, if it was the co-applicant's income with the applicant's income, we won't need to include both of them. So anything with a correlation of 90 some, anything with above 90% correlation, that's usually considered a very high correlation. So we look at the missing values, whether it's the loan ID, we don't expect that one to be missing. We see here gender, the number of dependents is missing 15, education is not missing anything, self-employed is actually missing 32, applicant's income missing nothing, co-applicant's income missing nothing, loan amount missing 22. So here is also another part that's usually also very important. So I will ask you also another question. How do you think we can fill in the gender variable if it's missing? In the gender variable if it's missing. So you can try that. How do you think we can fill in the gender variable if it's missing? So basically, I don't know if anyone is willing to try that. So for gender, for anything that is categorical, we are going to do a mode. A mode base is the most common. The most common, for example, for gender, we just fill in most gender variables, those that are most common. For married, we also use the mode. Number of dependents, we will also use the mode. The self-employed, we will also use the mode. So we fill in most of those using the mode, and then we'll go to the loan amount. Loan amount term, basically it's like a month, 2 months, 30 days. So that one we also use the mode. So you just shift control enter. So the loan amount will use anything that has outliers. We'll mostly use the median. The median is usually the best measure for outliers, as it's not usually affected. When you calculate the mean, it is usually affected with outliers. For example, if I have one up to 10 and I have 1,000 in there, when I calculate the mean will come to around 500 or 100. Since they are around 10, it will come to 100. But when I do the median will come up to 5, since I'm just taking the most middle value. So the median is usually the best when you are dealing with variables that have outliers. So we'll fill in the loan amount using the median value. So we'll check how many are null. So we have filled in all the missing values here. Also, we'll fill in all the missing values in our test data set. So outlier treatment. So outliers, as I had previously told you, there are those numbers that are usually huge, and we usually expect them mainly in the amount, let's say loan amount, the salary, the co-applicant's income. Usually expect a lot of outliers there, as outliers are usually normally because of, let's say, you are a graduate or you have a PhD, your income is much more likely to be higher compared to somebody who has just come from campus. So we usually have to treat outliers, and one way to reduce the skewness will be to take the log transformation. So log transformations usually they usually reduce, like, let's say noise. Noise is basically the outliers, the difference between the, for example, if I take the log of 100 and the log of 10, the difference between the two is usually not that big compared to when I take the numbers. That's why I usually take transformation for mostly numerical variables. So I don't know if anyone has any questions up to there. Any questions? So when you the log transformation for the loan amount, let us just compare it with what we are run up here. Yes, this is the loan amount. As you can see, it was skewed here, but when we transform using the log, you can see here that we have been able to reduce the skewness here. So basically what we are trying to do is to reduce the difference between the huge amounts and the low amounts, since most algorithms will act at that difference and take it to be very significant. So yes, Susan. So basically what I mean by, if you have a very high correlation, it means both variables are basically giving the same value. The same value when you apply it in a data set. One might be like, for example, let's say, how do I put it? Like for example, if you are using the co-applicant's income and the applicant's income, if their correlation value was very high, it means basically they're just giving us the same information. So we don't really have to include it when you actually run the model. I don't know if I've been very clear on that. So we'll get to the building the logistic regression model. So logistic regression is basically a classification problem. It's just binary, either it's a yes or a no, or a true or false. That's basically the logistic function. It's an estimation of the logit function. The log odds in favor of an event. Basically, what we mean by the odds, let me ask if anyone knows how to calculate the odds. How do you calculate odds? So, Tim.
Yes.
Hello, Tim. Can you hear me?
Yeah, I can.
Yeah. So, I was asking, since we have been able to run up to 920.
Yeah, so I think you can summarize there.
I don't know if
room for some questions. You can start with the next topic, because I know you are halfway through the script.
Yeah, I think
guys time to run experiments.
Yeah.
And play with this coming Saturday.
Yeah.
Yeah. So maybe just summarize then through, then open the.
So Okay, let me just summarize. But basically, what's remaining is just running the model. So we have done up to the outlier treatment. So most of you can now see why we usually spend a lot of time here on the working with variables and looking at correlation matrix and so this thing, especially the total income. As you are able to see here, we are able to get a clear risk separation. We are able to see a clear risk separation when we add the total income compared to when we just use the co-applicant's income. So what I would like for you to do is try and create, especially the binning part, try and look at some of the bins and see whether you can infer anything from most of these bins that I created, or what do you think about the bins? They are either big or we can actually reduce them. I think we can end there, as we can go to the next. Our next session will be on just running the logistic model, since I would actually love to explain this part separately from the feature. So what we have basically done up here is usually what you will be doing when you're doing feature engineering. So feature engineering is when you are designing your variables to be used in the model, and it's usually one of the most important parts. Actually, most of your time will be spent here in feature engineering compared to running the model, as the kind of features you will use will actually determine the accuracy of your model. Whether you add certain features or not, it will actually determine the accuracy. And adding creating your own features that were previously not there might actually increase the accuracy. So that's all I wanted to say up to that part. So the next part will just be working with the logistic model. And also maybe in another class we'll be building the logistic model on Excel, because I feel like when you do it in Python, you don't actually get to see how the mechanics, how the model actually works, and how to maybe make your own model, or like code your own model from scratch. And I also feel like you'll be able to better model. So I'll end there and leave the model building part for another session.